Greetings, this is Artie from Artifact Electronics. In this episode we'll have a look at this power supply, an electrophoresis power supply. It's kinda, when you're looking at this thing, it's a plastic case. The lettering on here looks like dry transfer lettering. I don't think this thing was built in very large volumes, but I found it at University Salvage and looked intriguing enough to get it and see. I mean, to go home, of course, figure out what electrophoresis is, and then see if it's working. So my research tells me that electrophoresis is defined as the movement of charged particles in a fluid or gel under the influence of an electric field. So I think the electric field is where this guy comes in. He will provide the electric field. Now that definition didn't mean a whole lot to me, so I dug a little deeper, and what I came up with was a technique used to separate charged particles like DNA according to size. Sounds intriguing, doesn't it? But before we delve further into it, let's carefully read the warning on front. There's danger, voltage, blah blah, can be fatal. What they should have added, this thing is really heavy. I mean, if you drop this on your head, that'll probably also be fatal. I mean, forget that. If you drop it on your foot, it'll be fatal. Weighs quite a lot, but as I said, it's a plastic case, and let's have a quick look here at what it does. But I can still hear some of you asking, so how do you separate DNA? You asked for it, you got it. I will give you a totally high-level, non-accurate, quick description. But the way it looks like is you take a non-conductive tray, such as this, you fill it with gel that is of the proper chemical composition, of course, and there's also some dye in there, and then you put a DNA sample over here. It'll have two electrodes that you hook up to the power outputs on this. Give it some juice, and if all goes well, you will see the DNA start migrating from negative to positive, and in the end being sorted by length. So you can basically separate a DNA sample into its constituent strands, and they'll be nicely sorted for you. And it looks kind of pretty, you know, depending on the dye. You'll have lines of different lengths appearing at the bottom of the gel here. And that's as far as I'm going to go with the biochemistry part of the whole thing. Because what we're going to do here is we're not going to worry about the application too much anymore, but we're basically going to treat this thing as a high voltage power supply. This unit was made by the Northeastern Scientific company in Boston, Massachusetts. It's a Model 101, and I couldn't find any sort of information online for it. I think there were one or two for sale, either on eBay or private sites, but as far as an operating manual, a description, or a service manual, I admit I did a quick search, but I really didn't find a whole lot. So after everything's said and done, though, just observing the front panel pretty much reveals what this does. We have a voltmeter that'll go up to 2000 volts. We have an ammeter that'll go up to 200 mils. We have a dial here that is the output adjust dial, and it's graduated from 0 to 100% of maximum. And of course, I'm guessing that the maximum is 2000 volts on here, so we'll find out. It's got a power switch and a light. Outputs, 4 pairs of outputs, which are probably wired in parallel behind the panel, and a standby switch, which enables or disables the output. Other than that, if we look on the back, not much more happening here. A few stickers, vent, serial number 376. But, you know, that's something that has always amused me about serial numbers, because you have no idea how they started numbering. I mean, what was the first serial number they put out, and what was their incremental interval for subsequent units. So this serial number doesn't really mean anything. I think what it does mean for sure is they built less than 400. I mean, when this was built, this was you know, the less than 400th piece they built at most. We've got power cord coming out, and if we look at it closely, we can see the fuse holder doing phantom movements. There's no strain relief on here. It's just a hole, slightly larger hole drilled through. Remember, this is plastic. So you won't be picking this up by the power cord. So let's have a look and see. Before powering up, let's have a look, see what's inside. Let's see what's inside then. I removed 8 screws. And here's our unit. Let's see. And I basically just observed this, looked at it, and there's not a whole lot in here. First thing I can tell you is there's no regulation here. We're going to have a wildly varying output depending on the load. But to go through the details, we have, let's turn this thing over a little bit to get a better view inside. And we have the AC coming in. Oh, the reason the fuse holder is moving is because the nut is loose, which I'm going to have to tighten. Problem fixed. So the AC comes in, and it travels through the massive power switch over here, which in turn feeds the AC to this auto transformer or variac over here. The dial in front changes the turns ratio in the variac, and that in turn is fed to this large transformer, large and heavy. This is probably these two guys are why this thing is so heavy. And it's a step-up transformer, so it takes the input, which should be between 0 and, in my case, 120 volts, and this steps it up to between 0 and 2000 volts. AC, of course. Then it is filtered, or smoothed, I should say, throughout these four. I mean, first it is rectified here, and then it goes through these 4 capacitors. But you might say, wait a minute here. We can clearly see that these Sprague atom capacitors are rated, have a capacity of 20 microfarads and 600 volt DC voltage rating. So how do we get 2000 volts out of this? Well, what you can do is you can actually increase the voltage rating of capacitors. This is something that I've seen used a lot in tube amps. And diagram would probably help, but if we look at this, and again, I'm guessing that it's wired like this. I didn't actually measure it, but I'm pretty sure that that's the way it is. So you have your 4 capacitors in series here, but you also have these equalizing resistors over here. And what they do is make sure that the voltage across each of the capacitors is equal. So that if we put 2000 volts into here, we will have an equal 500 volts across each of these capacitors, which is well below the rating of 600 volts. The downside of this kind of an arrangement, of course, is that capacitors in series, the resultant capacitance is always going to be less than the smallest capacitor in the chain. In our case, they are all labeled equivalently, and so if C1 through C4 are 200 microfarads, if we run it through this formula, the equivalent capacitance is going to be 50 microfarads. So you're getting 50 microfarads of smoothing capacitance here, which doesn't seem like a whole lot to me, but I guess this thing works. Well, I guess it worked at one point in time. So again, it doesn't look like a high volume device here. So here's my guess, and I'll be happy to hear comments on it, but it looks to me like a bunch of biochemists and electrical engineers at MIT got together and said, hey, we need an electrophoresis power supply, let's throw one together. Then other people came to the lab and saw it and said, hey, we want one too, and then they decided to go into business for themselves. Because, yeah, pretty much everything is off the shelf. I would guess that the case is also an off-the-shelf case that they used. And if you look at the manufacturing, for instance, you see this edge here. I mean, it's like somebody broke these PC boards. They scored them and then broke them off to make separate PC boards and stuff like that. But let's see, what else can we see in here? There really isn't a whole lot else. As I said, there's no regulation in here. This is it. You got a limiting resistor, and you have two diodes here that rectify and smooth the output voltage. And as you turn the wheel on this, the output voltage will vary. A couple of nickel and dime components here to limit the current going to the meters, both here and here. And that's about it. That's all she wrote. So let's see if she actually works. So while poking around in here, one thing I noticed were these capacitors didn't seem to be rigidly attached to the PC boards. I mean, they wiggled pretty good. So I removed the mounting screws for this board, and I guess it's not a PCB at all, but everything's point-to-point wired on the back in a sloppy fashion, I might add. And this brown stuff you see on there that almost looks like rust isn't rust, because obviously the phenolic board here can't rust, but it's some sort of goop they put over the whole thing. Probably some sort of dielectric to protect the connections and to prevent arcing. Let's go ahead and measure the caps first. Let's see. Okay, so first cap comes in at 20 mics, 2.6 ohms ESR. Number 2. Comes in at 19.6 with 3.5 ohms ESR. Oh, come on. $20.77 at 3.1 ohms. No. $20.16 at 3 ohms. These caps are still good. Yeah, I can hear you. They can't possibly be good after almost 40 years, but they read good, so I'm going to use them. Well, let's see what's going to be coming out of here. So now we're still dealing with a no-load situation. I'm using the high voltage probe with 1,000 to 1 reduction factor through the multimeter. And first, let's see if how accurate these analog meters are. Even though it's not just the analog meters, but my eye's in position too. So I'll try to stand right in front of it when I'm or having a straight-on look for it on it when I'm adjusting the dial. Let's turn the dial down all the way. You may have noticed there was no isolation transformer in here, so I am running it through the variac, even though I'm not bringing it up slowly, showing just under 120 volts AC over here, and here we go. Let's make sure the output enable is off, and we turn on power to it. Light comes on, and I can hear some transformer buzz. I don't know how well you can hear it. It's not severe, but you can hear this guy buzzing. Oh, I just noticed the serial number that was on the back of the unit is also on the transformer. Whatever that means. So now we're at 0, and let's power up the outputs. The transformer buzz completely disappears, and it's outputting about 6 volts. So let me change my viewing position here so I'm looking straight at the meter, and turn it up to 500. That's pretty much on 500 by my point of view, and multimeter seems to agree. Good accuracy so far. Let's go to the next step. 1000. Not too bad. 1500. And 2000. So the meters agree, and so it's able to output a voltage. The problem we can probably see right now is this dial is sitting at 70% of total, and the output voltage is at 2 kilovolts. So obviously the lack of regulation really makes itself show at this point. And it looks like the no-load voltage has a lot of headroom. Now we have to be very careful with this because of the voltage rating of the caps, which we can probably exceed if we would just went ahead and turn this all the way over. But just for grins, let's turn it in the neighborhood of 80, and we can see that the voltage is still rising here. And of course the meter is pegged all the way to the right. So far so good. Let's turn this back down again. You can see the meter is lagging a little bit because there's no real load on there. I mean, this thing is like a 10 meg input impedance, so it takes a while for the voltage to go back down again. And even at 0, you can see that it's still sitting at 30 volts, but continuously falling. Of course, I forgot to read the small print. This video is purely for entertainment purposes and not a tutorial. So if you don't know how to handle high voltages, don't. Or at least don't do it based on this video. And just be entertained by watching this. So next, of course, we need to add a load to it to see its real performance. Now I'm going to use a purely resistive load here. And for a load, I'm using this guy. It's essentially a 65 watt, 11k ohm resistor. How did I come up with this value? It was the highest resistance value, high wattage resistor that I have. I think I have 100 watts somewhere, but it's like 10 ohms, so that's going to cause havoc. So let's give it a try with this and see if we can get some current out of it, and then double check it with a calculator and see if it's actually if the numbers match. So we know what the resistance is, and we're going to know what the voltage is, and then we'll just solve and see, solve for the current and see if that matches up with what this meter says. Okay, off we go. This is at 0. Power is on. And output's on. So let's kind of turn this till we get to, say, 10 or 20 milliamps. And there's 20 milliamps. And so at 500 volts, well, let's set this, since we have an 11K resistor, let's set this to 550 as far as the meter is concerned. And if we solve, and at this point, this is a known, this is a known, the current is an unknown. So if we solve for the current, I is equal to V over R, which is 550 over 11K, which is 50 milliamps. So I guess this meter is accurate too. I'm going to be careful how much higher I go with this. See if this thing, yeah, it's beginning to heat up, probably because of the 500 volts. Now on resistors like this, it's holding steady, everything looks okay, but I'm going to dial back again. And the reason for that is, this is a surplus resistor. It does not have a voltage rating on it that I can see. But doing my research, high power resistors, wire wound resistors like this, usually top out at a 600 volt voltage rating. So let's not push it too far. But I think that showed us that we can actually, that it is outputting current. And we're not going to be, with what I have, we're not going to be able to measure. So how does this thing react if it's like in the 80, 90, or 100% region over here? Because with that high, I do not have a load that can tolerate a voltage that high right now. So I'm going to be satisfied that between 0 and 500 it seems to work, and that the ammeter is pretty accurate too. Yeah, you all agree, right? Very good. So there are the results. It seems to work. I don't really have anything to test it with. I mean, to me this is somewhat similar to a CRT anode voltage generator, except of course it's probably too low by a factor of 10, because, you know, for a black and white tube we're looking at about, no, actually for a color tube I think we're looking at about 20 kilovolts. So I mean, for a black and white tube, like on the Atari Asteroids, it was looking for 12 kilovolts. So I guess I can't think of anything else to use on this to test it with in the higher voltage ranges. But I think the ranges that we were able to measure are good news. Shows us that this power supply works. Probably have somewhat limited usage on the bench. I guess you could use it to power some tubes. But, you know, a single supply for tubes isn't going to be enough. And I don't know if you can think of anything, if you can think of any good applications for a 2 kilovolt, 200 milliamp supply, let me know, because I love to put something together where I can test this thing to full capacity. But I guess for now, another instrument for the bench, and it came off the shelf. This was going to be a repair video, because normally when the university puts stuff on a surplus sale, it's, well, at least it's because they've been told by whoever uses it that it doesn't work properly anymore. But I guess in this case the thing was just too old. If my guess of late 70s, early 80s is correct, yeah, it's 40 years old, and the they probably, somebody goes through the spreadsheets and says, this thing is just way too old, I don't care if it works or not, off it goes. Anyway, I hope you enjoyed watching this. Please support the channel with a like, make sure to subscribe, and leave me lots of comments, and especially a comment about what can I do, what can I use to test this. I guess I could use a CRT tube, but it probably wouldn't even start conducting at 2 kilovolts, so we wouldn't see what's happening with this. But I'm sure there's those of you out there who can tell me exactly what to get. And no, I'm not going to buy an electronic load or anything like that. I'm talking about simple stuff like a resistor or something else, or some device, or maybe something that I even have, you know, some common test instrument that doesn't necessarily test the voltage, but a component of which can be used to test this at higher voltages and performance. Anyway, we shall see you soon. Have a good one.